Hello again, and welcome back to my computer vision series. Today we will be reading the source code for Denoising Detr, or DN Detr for short. In my previous video, I went into great detail about the algorithm itself, about the motivation behind it, how it works. Today we will set up our own training to actually see the model. We will debug the model, we will step through the code and actually read the source code to better understand all the different aspects. Here is the plan for today. So I'll start with the model lineage, and by that I mean if you were to start from scratch, not using any pre-trained models, not using models downloaded from anywhere else, how will you achieve the same result? Will you re-implement the same benchmark? And I realize now that it's quite important. So in computer vision, in object detection, it is relatively easy because most of the data sets are open source and relatively small. Most of the models are, again, open source. And they actually provide with a working example of how to start training, how to start it on your machine. That is not the case in a lot of other AI-related disciplines. So, for example, for image generation, you never know exactly the data set on which the model was trained, even if the model itself is open source. You never know different aspects like censorship that make sure that the final model as a product does not contain any risks associated with it, and stuff like that. So for today, everything will be easy. Data set is relatively small and available for everybody. The model is relatively small and available for everybody. Next up, we are going to look at how to actually set up the training, how to get the data set, how to download the model, install all the dependencies, and the tools I use to effectively read the code and debug it. And this one will be really similar to the previous models that I've talked about, like deformable Detr, DAB Detr, and so on. Then we'll read the code for denoising query construction, and then we'll look at the actual denoising loss. Okay, so let's talk about model lineage. As promised, in case of DN Detr and other related Detr models, everything is relatively simple. The model itself, the one we'll look at now, is trained on the Coco dataset, which is available for free on the internet, and I'll show you how to download it. It is only 20 GB, so it's relatively easy to just download it to your computer entirely and train the model on that. As a backbone, the model uses the famous ResNet50 model, the image classification model that was trained on an ImageNet 1K dataset. So we will not look into that one today, although I do have one video about this model specifically. But the dataset is also available for everyone on the internet, and it is 150 GB. So if you want to go through with that, you will be able to do that as well. And the model ResNet50 that is used as backbone, today we are just going to download the pre-trained weights from the PyTorch hub. But again, it is relatively easy to train one from scratch as well. And the code and the overall setup of the model is really close to the previous models of that kind. So the Detr itself, the deformable Detr, the DAB Detr. And because of this, I will skip a lot of parts and just focus on what is new now on the actual query denoising. And I will just refer you to my previous videos about models like DAB Detr and Detr in case you have any questions. Okay, now how to set up the training and the debugging setup. So first we'll need the actual model code, and I'm just going to Google DN Detr source code, and it points me to this IDEA research repository. So I'll need to just clone that and follow the installation instructions here. So I'm pressing on the clone copy URL to clipboard. I'm going to my Ubuntu machine. So because of the CUDA layers, the custom layer that is used here, in fact, it is going to be the same layer as in deformable Detr. Because of this, this model only works on GPU. So it will not work on CPU, it will not work on Mac metal performance shaders. You will need to have an NVIDIA GPU machine with the actual CUDA installed. So I have one here, fortunately. That's my local machine here in my house, and I just connect that using SSH to make it more convenient. So just clone the repository. Next, I will need to install some dependencies, which include CUDA, PyTorch, and I will need to set up the actual CUDA layer to compile it. So they suggest using Conda, and this is what I do. The requirements of different models might be self-contradicting, meaning that a package version used in one model might actually break another model. So it is better to just set up everything in isolated virtual environment so that your different projects do not mess with each other. So what I'm going to do is I will use miniconda to create a virtual environment first. So I'm asking for Python 3.10 and then PIP. Next, I'm going to just follow the installation instructions listed here. So PyTorch, Torch Vision. And the next one is going to be all the requirements. Also notice that you just use PIP command here. This is usually unsafe because you might have a bunch of Python versions on your machine. On my Mac, I have like 10 of them because every time you install a new Python, the old one is still somewhere there, and you can never be sure if you just call a PIP command to which Python it actually refers to. In virtual environments, in Conda environments, you are sure that the Python itself and the PIP always point to the same version, so this is safe. Okay, so the Conda installation is complete. Now I'm going to install all the requirements. Now I can see here that it fails for our PyCoco tools with some C++ errors. And I know the fix for one. This is actually a new one, but I know how to fix it. So I'm going to go to the requirements.txt file. This is the one that we are installing. And you can see here that we try to install PyCoco tools by just downloading the GitHub repository and building that. So this repository is 2 years old. The DN Detr model is 2 years old already. Back then, maybe that was needed. Now you can just install it from the pip repository. So I'm just going to modify it a little bit and try once again. And it worked. It worked. So here we can still see some warnings that are not really related to the model. It basically complains that some of the other packages that I've installed conflict with each other, at least nominally. And this is why it's recommended to always install stuff for different projects in different environments so that, here I see Snowflake, for example. This is certainly not for DN Detr. If you just keep them separate, they will not conflict like that. So we had a minor hiccup there, but I managed to go through that quickly. And it's actually really, really frequent case that you need to do deep learning, you need to do science, but half of the time you're just debugging some compilation errors in some of the packages that you're trying to install. So this is really common, and you need to understand how all of that works to be able to deal with that better. Okay, now let's proceed with the instructions that we have in the repository. So the next one is to compile the actual CUDA layer, the custom one that I believe is just the same one as deformable Detr. So we're going to change to that directory and just run setup.py to install it. And the next line here is some tests to actually test that the compilation is successful. The installation was rather quick, and now I'm going to test And we can see that the first tests are successful. So it looks like code installation is also successful. And now the final one has failed with CUDA out of memory error. So this is the slight suggestion that on my machine with my GPU, I will not actually be able to train the full model because I don't have enough memory. So the entire training will not go through, but I will still be able to train for a few iterations, which is enough to just step through the code, to debug it, to understand how it works. But yeah, if you want the actual real thing, you better get something more powerful. So now we are pretty much ready. And now the final one is to just get the data. And to do that, we just Google Coco dataset. The very first website is cocodataset.org. So I go to the dataset tab, download. It's all just open for everyone. So I need to get train images, which is 18 GB, validation images, and then train annotations, and all of that for 2017 version. So I already have that installed, downloaded and unpacked, and it sits in my folder. And so inside that folder, I've unpacked these 3 files, and now they have annotations, train images, and validation images. And I'm just going to remember this path and now actually launch the training. So here in the run section, they have some commands for evaluation of already pre-trained models. We are actually more interested in training our own models. So I'm going to copy this one. And now here, I just need to change the path to the dataset to something that I have downloaded and just see how it goes. And I can see that the train has started. Some iterations are going. So it is working. I will be able to debug it. That's cool. This is like the very first step, which is in many cases, it's much more complex than this. So I'm always glad when I manage to do that successfully. So now I'm going to do all the debugging in the Visual Studio Code. And I also want to have a Jupyter notebook so that I can execute my code more interactively. So I'm going to just touch sandbox.py and just put some stuff in there. Sorry, not .py, but .ipyb, which stands for Jupyter notebook. And just put some stuff in there. You can just get my notebook from the link that I'm going to provide and just copy stuff around. And so this is my working notebook. This looks really similar to what we had in previous videos about Detr, deformable Detr, and so on. So thanks to the fact that I just placed it to the same repository as the DN Detr model itself, I can basically just copy code from main.py, including all the imports, including the ones that are defined in the repo itself. I can just copy it and it will work. Apart from this little detail. Okay, one final hiccup. Right, so now it should work. Then I have some helper functions to plot the results, to plot the images, to plot the bounding boxes on top of that. This is all the same versions as I had in the previous models. Then I have my special Rx class that lets me initialize the command line arguments object without actually passing in any command line arguments. And I just copied all of these from the debugger of the main function. And now if I initialize the object like that, I can pass it around similar to how it is done in the actual main.py. So if you see here, the main function starts somewhere here, and it just receives these args as an argument. And we can see that in a lot of cases, it just constructs the data set, build the model, just passing in this args argument. And thanks to the fact that I have this object, it works exactly the same way as actual command line arguments. So I can just keep copying the code around and everything will just work. So I'm just quickly going through the data set. I can plot the shapes of the images and see that they are indeed quite high resolution images. All of the slightly different size. This is how it actually looks like. So some objects, some bounding boxes around the objects. Next, I'm defining the data loader, which now takes in these images, and in some cases, it will also unite them into the batches. In our case, the batch size is just one, so it's not really doing that. But for the actual training, you might have a batch size that is greater than one. And in this case, you need to have some padding for the images to convert them to the same shape. This is how I can just grab some objects from the data set, just see how it looks like. This is a nice image with a lot of objects on it. And this is actually good because, as we'll see later, the denoising queries that we pass around, the number of those is actually dependent on the number of objects in the picture. So it's better to have uneven number of objects, like untrivial. And so in this case, we have like 37 of them. That can be right. Let's see. Shape. Okay, so we have 7 objects. So this is quite all right because it's not the same as batch size. It's not the same as anything else. So it will be just easier to read the code if you have 7 objects than any other number. Here again, we just build the model. All this is just copied from the main.py. And here is where stuff is a little bit different. So now, since the model actually uses targets in training, not just to compute the loss function, but to construct the input to the model. Now here is the first thing that's actually different, right? So here, the samples is just the images that we had. We also have the targets, and we construct this denoising arguments object that basically receives the ground truth objects themselves with labels and bounding boxes, and a bunch of constants like the number of groups, the level of noise, and all of that. And we just pass that to the model. So without that, this wouldn't work. And now thanks to this, I can just click here, launch debug cell, put some breakpoints somewhere, and just iterate through the code. So it's by far the most convenient way to read code of unknown models. Okay, so we have seen how to set up the training, how to get the dataset, get the source code, install all the dependencies, launch the training, and then have our own debugging Jupyter notebook that allows us to look at the actual images, to launch the code more interactively. And now let's actually start reading Denoising Detr source code. So Denoising Detr is basically a technique on top of DAB-Detr to add a special sort of queries and a sort of loss to just help speed up the DAB-Detr. Sorry, not speed up, but help train it better. So at inference time, they are almost the same model. So the first thing we are going to look at is just the construction of these denoising queries. And this is the reminder from the previous video about how this more or less works. So this is the decoder layer. So the backbone, the encoder, all of that comes from the left. So this is just feeding into as a side input to the decoder layer. And so in normal DAB-Detr, we have something called a target that is actually just initialized as 0, coming in as a first decoder layer input, and then for the second layer and so on, this is going to be replaced by the output of the first layer, and so on. In this case, instead of these zeros, we have the special unknown class embedding, and from the bounding box input, we get the priors, we get the anchor boxes. And these 300 queries, they are there during inference time, they are there during training, and they are exactly the same, well, apart from this class embedding as in DN Detr. Now, on top of that, we also want to add special denoising queries that are going to be connected to a different sort of loss. And so these denoising queries, instead of anchor box priors, they will have the actual ground truth bounding boxes as the spatial input, with some added noise to make it challenging for the model. And instead of unknown class embedding, they will have the real class embedding from the real class of the ground truth object, but it will also have some noise in it. So I'm going back to Visual Studio Code, and here I am at the very beginning of the model in the forward call. So let me just print out what I actually have here. Samples is a nested tensor because of the padding that in some cases we need to do if we have a lot of images in the batch. And I can just access the actual content as samples.tensors.shape. And so I can see that in this case, I have just batch size of 1. I get one image with 3 color dimensions, and then the resolution of 672 by 996, right? And this is the uppermost model of the model. So it is going to apply the backbone, transformer, and that's it. So let's just quickly read through that so that we have the general understanding of the model. So first, the backbone. So the output of that is the features. Okay, it is a list. So the features is now projected down to a smaller resolution, 21 by 32, but it now has much bigger number of channels. And then the positional embedding is basically the sine cosine embedding for the position of every pixel. And it has the embedding size of 256. Then we have the embedding weight, which is just the trainable anchor boxes. Let's validate that there are, right? So nn.embedding is just a randomly initialized trainable vector of parameters. And the shape of that is 300 by 4. So we have 300 anchor boxes as a priors for the object that we are going to detect, and each of the anchor boxes have 4 coordinates for x, y, height, and width. Then we do these prepare for denoising. So this is the primary function that we will read today. But let's just step through it right now and see the output of that. So I get this input query label, input query bounding box, and then attention mask and this special object mask dict. So the first 3 are fed in directly into the transformer. So query label is passed in as a target here. So this is like the content part of the decoder input. And its shape is now 335 by 256. And the query bounding box is 335 by 1 by 4, right? So what has happened here? We had 300 queries to begin with, 300 normal queries, not connected to denoising. Then on top of that, we have added 35 special queries. And 35 because, if you remember, we had 7 objects in the picture. And for each ground truth object, we are going to generate 5 denoising queries. So the total number of denoising queries is going to depend on the actual number of ground truth objects on the picture. And In our case, that's 7. So 7 times 5 yields 35. And so we have the content part with 256 dimension. We have the bounding box part with 4 dimensions, and then just the attention mask that we'll talk about a bit later. So then we pass that through the transformer, and as usual, transformer output is the same shape as input. So we got 335 queries in, and that's how many outputs we get out. Then we have some code to basically deal with the reference points. So this is the part belonging to the DN Detr, and basically we have 6 layers. We want to connect all 6 intermediate outputs to the loss, and because the reference points are actually bounding boxes, so we just project that down using bounding box embed to get that output, and that's pretty much it, right? So we got our, and that's also the 6 here as well. So we get outputs from all the intermediate layers. So we project down all the outputs using the class embedding to get the class predictions. We already did that with the bounding box predictions, and that's it. So we just output all of that. And then the mask dict here is basically a way of Denoising Detr to store some information in the transformer that is not actually used anywhere in its code, but it is then used to unpack the result. So basically, if we look at the diagram again, we had this transformer, the decoder, that is not really aware that some denoising is happening. It just receives a sequence as an output and outputs the same sequence. But internally, we keep the information that these 300 queries are normal, these 35 are special, and then the normal ones are going to be connected to the bipartite matching loss later on, and the special ones are going to be connected to the denoising loss. And this is the end of the function. So now let's break at the very beginning of this prepare for denoising function, and just do the same once again. So I've stopped on the transformer, and then I'm going forward to the prepare for the denoising, right? So let's read the argument first. So we have the DN args, which have all the targets as well as all the parameters of denoising. We have this embed weight, which are just anchor boxes. And then again, just some parameters like batch size, is it training or not, right? And so on. So this code will work differently during training and during inference. So during training, we actually know the targets and we actually construct the denoising queries. During inference, we do not know the ground truth objects, and we can't know them. And so we just skip them, and the model still works, and it outputs basically the normal queries only, and the predictions are still correct. So this is what happens here. So first, we deal with the normal queries, right? So there are going to be 300 of those, right? And this is how we construct them, basically. So first of all, I have this indicator 0, which is just one coordinate that I'm going to store in the embedding that actually tells the model, the decoder, if this query is normal or special. So this is just to help model understand what's going on. So then we have this label encoding. Here it's actually passed externally. Let's look where it's coming from. Okay, so it's coming from the actual transformer model. And this is again just nn.embedding. So it's just a random trainable vector. And the dimensionality of that is 92 by 2055. So we get 2055 instead of 256 because we are going to concatenate that with our special indicator variable, 1 or 0. And then 92, that's 90 for the actual Coco dataset classes, so person, train, pizza, and so on. 1 for no object, and 1 for unknown object. So here, all the targets receive this num classes as the lookup. So if we just execute that and just see what it is, it's just a constant number, 91. So 91 is going to be equal independent on the image that we get in. So it's like a constant that basically encodes the unknown class. So no other targets will have this class of 91. So this is the way to encode this unknown class, basically. And so now I pass that through my label encoding. And so the target shape is now 300 by 2055. And then I concatenate that with our indicator, and now it's 300 by 256. So this is how I got my content embedding part, content decoder input. So it's, I would say, a projection of a known class, but basically the same as saying a trainable vector that is equal for every image, and the anchor boxes that I've received as an input. So this one has the shape of 300 by 4. Okay, so this is my input for the queries, for normal queries, right? So next I will need to construct the denoising queries, the special queries. So a bunch of this code is really maybe a bit hard to read because it actually deals with batches where you need to remember which object, which query actually comes from which image, and so on. But then, yeah, it's not really that interesting what is happening here. But it's clear from like what you get as an output. It will become more clear. So this part is interesting. This is where we add the noise to the label, right? Now, known labels expand, come from known labels, which in turn come from labels, which in turn come from targets, right? So this is what we got as an input. So the actual ground truth objects. So we generate some randomness in the same shape as our labels, which is, in our case, 35, right? So 7 objects, 5 groups. Then I compare this with a constant, which basically defines how much noise do I have, right? And choose some indices to flip, right? So I had 35 objects, so 7 ground truth objects multiplied by 5, so 5 groups of 7 objects. 8 of them I'm going to flip, so I needed roughly 20%, so I rolled the dice and chose 8 indices to flip. Then I'm again generating random indices for the flipped ones, and then I just replace what I had initially with those flipped indices, right? So we can try to compare what we had, right? So the actual 35 numbers for the objects. So 37, 37, 37, 37. So 5 times 37, a bit more times 1, and then 40, and so on. And then after flipping some of that, yeah, this is already after flipping, right? So I should have printed it earlier, but nevertheless, I think this is pretty clear. So we had 7 objects. We repeated that 5 times for 5 groups, flipped random 20% of that. So 80% of these will actually correspond to the object that we had in the picture, and then 20% will just have random class. Then I do box noise in a similar fashion. So I just generate some noise, add that to original bounding boxes. I also do this clamp to make sure that they are indeed still inside the picture, right? So there is a good way to print out what is happening here. So I had my bounding boxes, right? 35 of them. Let's print the first 5. Okay. And now here I'm multiplying by quite a huge noise, 40%. So it's going to be a bit harder to read. So instead of multiplying that by 40%, let me just take 4% instead and take the first 5 again. Right. So I had my bounding boxes, which stands for XY coordinate, height and width. And then I added some noise to it, right, to make the task a bit harder for the model. And that's it, right? So far, that was just transformation to the ground truth boxes, right? So now I have my noise labels and noised bounding boxes. Now I need to encode that into the actual embedding, right? So bounding boxes should be fed into the decoder as is, because bounding boxes in DN Detr are decoder inputs. And I also need the label embedding. And for that, I need my label encoder, right? So now M here stands for the actual classes, the noise classes that I had. And you can see here, so above I had unknown class that was always equal to 91. And in here I have some numbers like 1, 37, 40, and so on. But sometimes it can be 1. So 1 is a person, I think. So now I have these various classes, and I use the same random trainable vector, 1 per each class, to encode that. And now I have this encoding embedding, which is 35 by 255. Now I have my indicator 1. So for normal queries, I had indicator 0, and then for the special queries, I have indicator 1, and I just concatenate them. So this is how I cooked my content input for the special queries. It's now 35 by 256. Right. This is pretty much the logic of creating the denoised queries. And now I just concatenate it all together. Right. So let me scroll down a little bit and just show what are we actually returning. Right. So what we actually return here. So we turn input query label and input query bounding box. So by now, input query label is 335 by 256. So this is the content part of both 300 normal queries and 35 special queries. And then bounding box is the same, but only 4 coordinates. Right. So this is basically the majority of the model, to be honest. I also need attention mask. So a reminder, the whole point of attention mask is to prevent information leakage that we can't afford to have due to various reasons. So one such reason is that in here, we are actually feeding in ground truth boxes to the model as an input during training. And if we train it in such a way that the part that actually does object detection has some access to ground truth boxes, then it's just going to spoil everything. Because during inference, this object detection part will not have those ground truth boxes, and it doesn't really know how to deal with that. And so the model will just output some random stuff. Similarly, we can't have different denoising groups looking at each other, because the task of denoising group number 1, for example, is to get some noised version of the object and then to remove the noise. But if you see a different noised version of the object, it just makes the task easier, right? So if you have like 5 groups, you can just average out and maybe get a pretty good understanding of what is noise and what isn't noise. So in attention, we allow the group number 1, for example, to attend only to different objects within the same group, or to the normal queries, to the normal detection part of the model. Similarly, for the group number 2, we allow to look at all the objects within the group and to the 300 normal queries, but not to group number 1, and so on. And so this is what happens in this code, right? So its color here is 5. So here is how we prepare this attention mask. So maybe let me scroll a bit further and just try to print the result, right? So now the attention mask is 335 by 335. Right, so let's look at the first query and the first 45 objects that it attends to, right? So in the attention mask, false means that you are allowed to look there, and then true means that you just basically make it invisible. You are not allowed to look there. So I had 7 objects. So the first 7, this is so annoying in Visual Studio Code. The first 7 are false, so this group basically can look into the objects of the same group. Then I should have something like 28 objects that I'm not allowed to look at, and then again a lot of falses. So actually, let's just look at all of them, right? So most of them are false, but then this group is not allowed to look at second group, third group, and so on. But it is allowed to look at all the 300 normal queries. Similarly, for query number 8, for example, so this is the second group. So it skips the first 7 because this belonged to the previous group. It's allowed to look at object 8 to 14. So this is the current group. Then the next 3 groups are again skipped, and then the normal queries are all allowed, right? And then object number 100, for example, that belongs to the normal part. It is not allowed to look at any ground truth object or any special object, so all of them are true, but then all of the 300 normal queries are still false, right? So this is the attention mask. I also have this mask dict, which is again the object that is just passed around with some useful information, and that's it. That's what I return. So this is like normal queries, 300 of them, 35 special queries that I cooked using ground truth labels, ground truth bounding boxes with some added noise, and then encoded using my label encoding, the indicator, and so on, to turn that into embedding. And now what I have here is indistinguishable from the normal queries. So the transformer code, the decoder code, is going to be exactly the same as for DN Detr. So it just receives 335 queries now and just outputs all of that. Okay, so we've talked about how these denoising queries are constructed. Then they are passed into the actual decoder, the transformer, and the code for that is exactly the same as in DN Detr, so we will not stop on that. And now we just look at the loss. So now we got those outputs out of the transformer, and now part of that will go to the normal bipartite matching loss, and another part will go to the special laws for denoising. So let's look at that. So similar to how I got my model outputs by just calling the model, I can just get the loss output by calling the criterion, the loss, and I can put some breakpoints in. They should be able to read it. Right, so the loss is being constructed as part of the model. It's constructed here as a set criterion. And let's just, so it's also an nn.module. So I should set a breakpoint at straightforward method, right? And then I just launch this cell with the loss calculation. So I already have the targets. In fact, let me just print out the shapes of that. Just to remember, right? So I've already separated, by now the normal queries are already separated from the denoising queries. So now the outputs in themselves look exactly as the ones for Detr, and the special queries are separated into this special mask-dict object. So the first element here is probably the class predictions, the logits, and then the second element is the actual bounding box predictions for the noise queries. Right, so then I just press debug cell, and I am inside the loss function now. So again, outputs here are the normal queries that work exactly the same as in normal Detr, in fact. And then this mask-dict object has everything related to the actual denoising queries. So let's just see where that is used. So this is used in this special function called compute DN loss, which is then passed into the losses themselves. Right? So let's just go to this one and also break here. Right. Now I unpack this mask-dict object. Let's look at this prepare for loss function. So I get out the actual outputs, output class probabilities, output bounding box coordinates from this part, output known LBSB boxes. So yeah, I'm basically just unpacking the dictionary here, doing some permutations to make that work with the loss that we need, and that's it. Output of this function is now known labels, which stands for ground truth. Output known class, which stands for logits for the classes, and the same for known bounding boxes and known coordinates. And then I calculate the loss, and I have two losses here. So one is for bounding boxes, one is for labels. Let's read both of them. They sound pretty easy. So the one for labels gets the logits predictions, gets the target labels, reshapes them to make them compatible, and then computes this sigmoid focal loss. So the focal loss is a slightly modified version of binary cross entropy that basically modifies how easy and hard example, how exactly they contribute to the loss. And then the second one here is target loss boxes, which now has two parts. So L1 loss, so basically the distance between the ground truth boxes and predicted boxes, and the generalized IUU, so intersection over union. And this is really it, right? So we had our 335 queries. We got 335 outputs out of that. The first 300 went into the normal Detr loss process, where it goes to the bipartite matching loss. It gets connected to some outputs or an object. And then the special 35 queries, and the number, of course, is different depending on the number of ground truth objects, is going to be matched with the ground truth objects themselves, and we'll actually see how well the model performed at removing the noise and at predicting the correct classes, knowing the noise class. So this is really it. It's relatively straightforward, and I repeat again that the main change of this model compared to DAB-Detr is just in a way we construct these queries, add noise to them, construct the embeddings out of them, and how we then use that in the loss. So the actual transformer, the decoder, the attention that is modulated by bounding boxes, all of that actually uses exactly the same code as in the DAB Detr. So I hope this video was useful. I hope that it helped clear out some doubts about Denoising Detr, and maybe just allowed you to run it yourself and just read it and understand more. I also want to take a moment to just tell a bit more about my channel. So apart from just making videos about random stuff, I try to put them in a certain order to make it an actual learning path. So recently I was focused on modern object detection. So I've started with a famous algorithm called YOLO, which is a bit more old school and uses convolutions. Then the Detr family of models, which are now really popular for object detection. So I've talked about Detr, I've talked about deformable Detr, DAB Detr. I've read the code for all of these, and now the Denoising Detr and reading the code for that one as well. And the next video is going to be about Vision Transformer. So this is slightly different now. Vision Transformer is not really about object detection, but just about image recognition. It is basically going to serve as a backbone, as a transformer-based replacement for ResNet 50 that we had today. Then I'm going to cover a different transformer version called Swing. Both of these are used in the famous model called Dino, which combines the improved backbone with denoising Detr and some extra techniques on top of that. And then finally, the current state of the art called CoDetr, which also inherits heavily from all the modules I've just described. Apart from that, I also have a more introduction class where we start with just the simple digital classification with some dense layers, and then discuss a lot of basically deep learning foundational concepts like initialization, activation functions, weight decay, learning-based scheduling, and so on. And I also have a branch about about generative AI and image generation. So the first video is already out about neural style transfer, and I'm going to make more videos about some advanced concepts like operational autoencoders, diffusion, stable diffusion, and all that stuff. So hope to see you soon.